Make models learn faster with proper feature scaling. By the end, you will know when to use standardization versus normalization. See how scaling changes nearest neighbor results, and build a tiny k-nearest neighbors baseline on scaled data in Python. You will also understand one quick rule of thumb to pick a scaler for a given model. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Feature scaling is a small step that fixes big problems. When features live on different ranges, models treat them inequally. A distance-based model can be dominated by a single wide-ranging feature. Gradient-based models will take uneven steps and converge slower. Success means better training stability, fairer feature influence, and more meaningful distances when you compare vectors. The trade-off is that scaling removes the original units, so interpretability drops a little, and you must apply the same transform to new data. Intuitively, standardization centers a feature and rescales it so it has 0 average and 1 spread. Normalization squashes values into a fixed range, usually 0 to 1, so every feature shares the same bounds. Picture 2 columns, one in dollars and one in percentages. Without scaling, the dollar column can overwhelm. With scaling, both columns contribute on equal footing. Standardization is robust when you expect roughly Gaussian features. Min-max scaling is useful when you want a constrained range for algorithms that assume bounded inputs. We will build a tiny example that standardizes and normalizes a small tabular dataset, inspects nearest neighbors before and after scaling, adds L2 normalization for fair distance comparison, and runs a leave one out k nearest neighbors baseline on the scaled data. Next, we prepare the data and standardization setup. This snippet standardizes features to 0 mean and unit variance. It shows how to fit a standard scaler to the training columns and then transform both training and test sets the same way. But description explains that standard scaler subtracts the column mean and divides by the column standard deviation, and why you must reuse the same fitted scaler on new rows. It also mentions the optional behavior to skip centering or scaling, and that toggling those options changes how much the transform shifts or compresses the distribution, and can matter for sparse inputs. Now we will rescale values into a bounded range. This snippet rescales each feature to the 0-1 range. It fits a min-max scaler on the same training columns and demonstrates how the smallest value maps to 0 and the largest maps to 1. The paragraph explains when min-max scaling helps. For example, when using activation functions that expect bounded inputs, or when you want interpretable bounds for each feature. It also discusses the effect of clipping or using a different feature range. Changing the feature range alters the span of transformed values and can affect model sensitivity to small differences. Next, we check how neighbors change before and after scaling. This snippet compares nearest neighbors before and after standardization. It uses a nearest neighbors implementation to find the closest points in raw space and in standardized space, showing which records move into or out of the neighbor set. The explanation notes that distance-based methods like k-nearest neighbors and clustering rely on the relative scale of features, so scaling can reorder neighbors dramatically. It also points out that if you change the distance metric, such as switching from Euclidean to Manhattan, you will further change neighbor relationships and the sensitivity to scaling may differ. Next, we apply a length normalization step to make distances comparable. This snippet applies L2 normalization after standardization to compare distances fairly. It normalizes each sample vector to unit length so that distance compares direction rather than magnitude. The paragraph clarifies when this is useful, for example, when features represent proportions or embedding directions, and you want cosine-style comparisons. It also explains that applying L2 after standardization is a common pattern to first equalize variance across features and then compare vector orientation. Changing whether you apply L2 or not will shift emphasis from vector length to vector direction. Finally, we put it together into a tiny evaluation. This snippet builds a tiny leave one out KNN baseline on scaled data. It trains a simple k-nearest neighbors approach, where each sample is held out in turn, predicts its label from its scaled neighbors, and reports accuracy. The paragraph explains leave one out as an incremental test that mimics a realistic small data evaluation, and why consistent scaling before each fold matters. It also mentions that the adjustable parameter k controls the bias-variance trade-off, with small k producing more variance and larger k producing more smoothing, and that you can compare results between raw, standardized, and normalized inputs. To recap, feature scaling means standardization or normalization to make features comparable. Use standardization when features follow different spreads and you expect roughly symmetric distributions. A caveat is that scaling hides original units, and you must apply the same transform to new data. Next step, run the same pipeline on a larger data set. Add timing and accuracy checks, and sweep the k parameter to see how sensitive your baseline is to scaling choices. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.